Hi, I'm Oliver Gao. I'm the director of Cornell Systems Engineering Program. As I have been conducting this what I call systems conversations with our prestigious speakers that we brought to Cornell. So today, I'm very delighted to have Dr. Travis Humble to be with us. Travis is a distinguished scientist at Oak Ridge National Lab and a director of the lab's Quantum Computing Institute. Of course, now you hear quantum computing. This is really, I think at the frontier that a lot of people are very interested. Actually, Travis he received his doctorate degree in chemical chemistry, in theoretical chemistry from the University of Oregon before coming to I think Oak Ridge National Lab in 2005. He's actually leading the quantum computing team in the quantum information science group there at Cornell. So actually, he also oversees the research and development of quantum computing technologies. So I think this is wonderful background and topic, for our Ezra Systems Speakers series. So when I was reading your bio, and one thing that kind of interests me a lot, from a theoretical chemist and to quantum computing technology, that sounds to a lot of people quite a leap. And of course, I think that's really a very good, I think, example of like systems engineering. Of course, at this point, I think for both me and I think the audience will be watching this video, I think we're very curious to learn more about you, Dr. Humble. Would you like to start by talking more about yourself, whatever you want people to know about?
Oh, of course, yeah. No, I'm happy to, Oliver. Thank you. I really appreciate the opportunity. That's right. So I made the transition from a theoretical chemist in 2005 to working in quantum information. And you might think that that was a very big jump. But at the time, theoretical chemistry was very interested in how quantum mechanics could be controlled to drive chemical reactions and understand more chemical behavior. And so for me, the jump over into quantum information was really more of a change in how I looked at the problem, more as an information theory problem. And so I began work on quantum teleportation. This is a method of communicating information from one location to the other, uses entanglement between particles. That is also a feature that shows up in chemical systems as well. So the physics was not the hard part. What was difficult was trying to convince people that you can send information from one place to another without it traveling the space in between. This is what teleportation does. And so for me, the career took a very sharp turn there, picking up the concepts of information theory. And then that is slowly turned into an entire field of research, quantum information science. And my own specialty in that area is looking at quantum computing. How can we use these ideas to accelerate computation? But it's come a long way from the early days where I was making the transition from chemistry.
Yeah. That's wonderful. I think that's kind of, as you mentioned earlier, you can see that kind of even on a concept level, it's hard for a lot of people to realize that, as you said, the information or something can be transported or transmitted without even like a real transporting system.
That's right. Yeah.
Right. I think that's really amazing. I think this is probably since you just started this conversation, you talk about this. You touched upon quantum computing. I guess at this point, I would like to, if you can help us dive a little bit deeper into what is exactly quantum computing, and what is the strength. Basically, for me, for example, my work is in transportation system. Like I look at transportation and how transport impact air quality and then human health. Actually, along the way, there's so much computing that we need to do. Like for example, nowadays those kind of air quality simulation models. If you want to just simulate one scenario, it could take months, right? So kind of I'm also interested in learning more about this quantum computing. So what is the strengths and why quantum computing?
Right.
Yes.
So why quantum computing? It's an excellent question. It all started, I think, 35 years ago. Richard Feynman, a Nobel laureate in physics, made the observation that many systems of interest are quantum mechanical, chemistry, materials, high energy physics, and that our efforts to model and simulate those systems actually are challenged using conventional processors. In some ways, the theory behind those systems is very much classical physics. And so if you want to simulate quantum mechanical systems, try building a computer made out of quantum mechanical systems. This is what led to quantum computing. It's the idea, the theory of computation using the laws of quantum mechanics. And for the first 25 years, it was a very good theory. We had lots of progress in understanding how we might do this, designing abstract models of computation around quantum mechanics, even coming up with some breakthrough algorithms that showed that these quantum mechanical systems would greatly outperform conventional approaches to certain problems. Factoring integers, searching unstructured databases are two good examples. My own interest is in that they can also be used for simulating these physical systems, chemistry, materials. It's only been the last 10 years that we've made real experimental progress on having those systems come to life. We now have quantum processors that we can run some test problems on. They don't yet outperform our conventional computers. We're very close, but not yet. And they are still undergoing a lot of engineering, right? And I say this in the sense of both at the systems level, trying to understand what a quantum computer should look like at a systems level, but then at the device level, how the pieces, the components should be manufactured and processed in order to be reliable. And so there's a lot of open questions right now on how to build quantum computers, but the theory, as far back as 35 years ago, is what's driving us all forward.
Yeah, I think that's wonderful. It's really it made me realize again, as a frontier of some discovery, right? It's really it's an intertwined co-evolution of both theory and the physical world, and even technology. And I think thank you for sharing with me how this was initially started. My very simple interpretation might not be correct, but I'm thinking, for example, the traditional computing, right? Of course, we just based on it's dichotomy, it's 0 and 1.
That's right.
And a lot of calculation is based on 0 and 1. It's kind of dichotomy. But I think quantum mechanics, because actually there are more than two status. There are multiple states, right? It's again thinking about from going from a binomial to multinomial, right? So those kind of things. So, and you mentioned also that it seemed like is a theory for quantum computing ahead of practice or something, because it feels like this concept. I know you're saying nowadays that quantum computing in terms of computing power probably has not caught up with the traditional computing. But do you think this gap is that because at a very fundamental level these two different paradigms, is one paradigm not as good as the other one, or actually the paradigm of the quantum computing is actually theoretically much better than the traditional computing? However, it's just implementation level or technology level, we are there yet. Where do you think the gap could be caused?
Well, I think this is a great question. I think I would start perhaps by addressing the question of what differentiates quantum computing from conventional computing approaches. And foremost is that quantum mechanical systems can have properties, entanglement, superposition. These are formal statements about how you can express information. You mentioned, classically we think of binary states, 0 and 1. In quantum mechanics, the superposition principle tells me I can have an infinite combination of the 0 and 1 basis states to express information. And so now, whereas a bit can express one bit of information, a qubit or quantum bit can actually express an infinite number of possible quantum states. So that's what differentiates quantum from conventional approaches. But that is also the challenge, is that the ability to control quantum mechanics using classical interfaces, our classical electronic systems, optics, electromagnetics, actually has turned out to be a challenge for engineering. We get down to the level of sensitivity that is basically state of the art. in our electronic controls. And it turns out that the required sensitivity to control some of these superpositions may be just beyond where we are today.
Mm-hmm.
So pushing past that is as much an engineering problem as it is a theory problem. If I can come up with clever control mechanisms, either using some sort of feedback or error correction, then I can potentially maintain stability in my quantum systems in ways that currently aren't possible. Similarly, once I'm able to fabricate these systems with even tighter tolerances, then I can actually rely on them more. And so it's very much a trade-off in the design of new systems and the control of the existing ones.
I think thank you, I appreciate that point. It's kind of, 1 bit versus, a qubit.
That's right.
In a superposition. It's really kind of interesting because, from our research, as a researcher, right, we try to decompose a complex system and further down to its building block or its kind of element, of course, quantum mechanics, atoms or electrons, all those kind of levels. So somehow, however, you can see that qubit, as you said, qubit qubit can express different layers of almost infinite information from information from infinite combinations of bits.
That's right.
Right. So that can come from philosophic point of view. Some like a qubit is really some kind of mix all the bits.
That's exactly
together.
It.
So from a philosophic point of view, do you think like we should, because when we integrate things together, while it's more powerful, but it also becomes more complicated. So in that case, kind of from building a very fundamental mechanism for example, for computing, do you think like implementing things at the bit level versus implementing things at a qubit level, which one is on Earth better?
That's excellent question. So I definitely think that the control of the qubits right now is much more difficult. In some ways, bits have a very good design, right, using transistors.
Yes.
But the base technology for qubits right now is still very diverse. We have people looking at superconducting electronics, where you're controlling the flow of an individual electron, actually a pair of electrons, Cooper pair, within a cryogenically cooled circuit. We have trapped ions. This is capturing individual atoms with magnetic fields and trying to control the state of the electron in that atom. We have nitrogen vacancies. These are diamonds that have had an atom removed, and again, a lone electron is present, and we're trying to control that system. All of those are operating at the microscopic level. And so the ability to manipulate the microscopic physics that determines their state is what makes that so challenging. But it's also what opens up new opportunities.
That's
right? To encode information in new ways. I think that we are still looking as a community for the robust design of a based quantum technology. Current approaches are exploring that space, but I do think that there are theories proposed using what's called fault-tolerant quantum error correction that takes multitudes of these individual qubits and couples them together so that they are, in some sense, self-correcting, right? So if an error does occur, they can stabilize themselves. That may ultimately be the equivalent of of today's transistor. We're still many years away, I think, from seeing that on commercial products. But within the research labs, we're just now seeing them starting to build those types of devices. So I hope this was getting it.
That's great. Yeah. This is great. Thanks, Travis. Of course, you can see that any new technologies, it's earlier stage, right? It's we need people and we need great thinkers to not only take the risk, but also kind of try out all the different ways. And you talk about this control mechanism. So as you said, there are still many things that need to be addressed, and also there are a lot of uncertainty, which means there is risk. What makes this risk worse to take?
Right. Oh, excellent question. So I mentioned earlier that there were a few algorithms early on that indicated hypothetical quantum computers would outperform our best classical computers.
Mhm.
One of these is very well known as Shor's algorithm. It was invented by a gentleman named Peter Shor, and it's an algorithm that shows you can factor a number into its composite primes, an integer number into its composite primes in polynomial time.
Mhm.
The best known conventional algorithm on a classical computer requires essentially exponential time to do that. So there's an enormous separation in the complexity of these two approaches. Well, here's the kicker. That factoring algorithm underlies all of modern encryption. And so when you and I send confidential messages or we interact with our bank online, all of that's based on some sort of public encryption scheme, oftentimes RSA or something like this, that has at its core this integer factorization problem. And the fact that it could be done in exponential time on a classical computer is what protects us. You know, an adversary would not have enough time to really solve that problem.
Mhm.
But if you had a quantum computer that was of sufficient size and capability to run this algorithm, you could crack that problem in seconds,
Mhm.
which would immediately expose all of us, all of our protected information to release. And I think that alone has captured a lot of people's attention. Coming from the Department of Energy, what has motivated me has been the relation to scientific discovery. This very same type of arguments can be made about our ability to model and simulate chemical reactions, material science, and having the opportunity to simulate more complicated reactions than any supercomputer could do today means I can explore new types of battery technologies, new types of fertilizers for food security. All of these different types of capabilities suddenly become available with using a quantum computer. So that's one of the payoffs, right? Is
Yes.
that we'll suddenly have a new computational capability that even in our wildest dreams we'll never get with classical computing.
That's wonderful. So I think this is really kind of the further depths of this kind of discussion. So of course I can imagine you after you did your PhD and you did actually it's based on your explanation, actually it sounds like a very natural because you did the theoretical camp, and when you try to look into the further depths of how things can be changed or something that kind of probably actually kind of drove you towards the quantum computing, some exciting thing. Of course, I was just imagining, through the years. For example, since 2005 till now, like say, about 15 years, right? You're doing these things, and I assume that there were probably ups and downs. When you were pursuing this research and also for your career. So when you were in those downs, what things that kind of kept you still believe that quantum computing is a hope, not hype?
Oh, that's a wonderful question. I think the downs are always tough, right? I mean,
Yes.
This is where you really have to figure out, do you like this problem or not?
Yes.
But as a researcher, what was driving me was that I knew this problem needs an answer. Okay, I mean, this is still what drives me today. We've not found the answer yet, but the possibility that conventional technology, may eventually hit some sort of physical limit. I can only push Moore's law so far before I start trying to split the individual atom, and that's unfeasible. I think that the idea that humanity needed, or it still needs, alternative technologies for the 21st century is really what drives me. Even if they're very hard to figure out the solution, the fact that we need some sort of new technology base to continue pushing information technologies, computing, sensors, communications, that is, I think, an incredibly important reason why we do this research. It is, of course, not always the answer you want to hear. You want to hear that, no, the solution's right around the corner. But the truth is that this is a very hard problem with a very big payoff, and it's very much worth that effort. So.
Thank you. That's beautiful. I like your, the answer to the question. I think that's exactly something, and also I think this is probably one of the beauty, of some mechanism here in this nation where people are blessed to pursue things that they believe that excite them, right? So speaking of that, you're saying we have ups and downs. Of course, now if we jump out of this kind of theoretical realm and we come back to reality, and I think while you are trying to drive this dream forward and try to pursue, actually I think no matter what will come out in the end, which is already a very successful story because you pursued your dream. So now in the real world, what do you see as the major challenges and also opportunities for quantum computing, for the whole profession, for the whole, for the society of this quantum computing? Where do you see as a major challenge? What do you see as a major challenges and opportunities?
Oh, great question. I mentioned 35 years ago was when we probably first started thinking about how would we build a quantum computer. It has been a slow start, but it is currently ramping up with a lot of interest, not just from physicists, from computer scientists, from engineers, from application users. And what I see as being a major challenge right now is increasing the communication between all of those different communities. And this probably ties, I think, into the idea of a systems level approach. We understand that the engineering of quantum systems right now would benefit from some modularity. I talk about qubits, but the truth is I can't build a qubit in factory A and a qubit in factory B and put them together and have 2 qubits. It doesn't work like that right now. I need to overcome the modularity problem. But even beyond that, I need to better understand where quantum computers fit into our current ecosystem. And that requires a conversation with the end users. Coming from Department of Energy, scientists there want to use quantum computers for discovery, modeling, and simulation. Outside of Department of Energy, though, in industry, there's many applications that have already been specialized for what that industry does. Quantum computers do not solve every problem more efficiently. And so the question is, well, which problems that industry has today would benefit from quantum computing? We have to have that conversation even before the systems are built so that we know why we're building the systems. I think that communication is an important part. And then the second piece to all of this is that we need the workforce that understands the technology and understands the applications. Currently, quantum computing is really an expert's field. You need some sort of depth in physics, or at least quantum mechanics. That can come from computer science or electrical engineering. But we're going to have to lower those entry barriers because we need many more people involved in this effort. And so I think that that's an important step going forward, is looking to the universities to establish curricula or at least some types of education that can support workforce growth. So.
That's wonderful. Later on I was going to ask you about what this means for research and education. You already partly kind of brought that up. So with all those challenges and opportunity that you just laid out, so you've been really playing a very key role in many different sectors, kind of trying to push forward this quantum computing. Especially I noticed that you are serving on the steering committee of this IEEE quantum computing initiative. So I think that's probably I would like to learn more about, for example, your approach and also the IEEE initiative, because I feel that's probably going to be the place where you're going to put a lot of your thoughts, as you just talked about, into the real car to drive it forward. So what can you tell us more about your own approach and also the IEEE kind of initiatives in this area?
Absolutely. So as I was saying, I think that the getting communities to come together and work with each other is an important next step for the quantum development of quantum computing. The IEEE as a professional society has access to an enormous wealth of talent. And so over the last year or so, myself and 3 others, co-leads, have initiated within IEEE a quantum development effort. It's called IEEE Quantum Initiative. Has a website. It has had a couple meetings so far that bring together some of the experts in quantum computing to talk about what is needed for communities to come together. We're currently planning to host an even larger event in the future where we draw from experts across IEEE as well as academia and industry in the national labs around the world to have this conversation, just like we were talking about. What are the challenges, what are the solutions, what are the payoffs, and how do we get the right people working on the right problem? I do think that this is a technology that many people are anxious about getting started, and so I don't want things to slow down because the wrong people were talking to each other. I want to be part of that helps lower those barriers. So this is my role, right? I think in my goal to try and help establish these communities and enable people to communicate better.
That's great. So do you see any kind of lower hanging fruits out there?
Yeah, so I think there are, the lowest hanging fruit at the moment is getting people to start speaking the same language. And specifically, terminology is always the first step to a good conversation. And so getting people to understand what it means to be a quantum computer, even the basic ideas of qubits and superposition, that's where we start. And over time, we'll eventually become more sophisticated. We have a group within IEEE looking at metrics and benchmarks of quantum computers. How do I measure performance? Not because I want to show that it's better than anything, but I want to know if I'm making progress. And so we have a group of experts, probably on the order of 24, from around the world, coming together. And the first thing that we all did was we said, well, what do we mean by a quantum computer? And so we're slowly working our way through these types of questions. But that's the important first step, and that's what eventually gets us to answering that.
That's great. I think that's when I asked you about kind of the key initiative or key challenge, you talk about communication, and of course I think at the core of communication is that people speak the same language, and you mentioned the importance of this terminology, and I think it's really very nice kind of system thinking about dealing with these challenges. So with this, and also I think earlier you mentioned that so far quantum computing, so far it's kind of more like kind of expert domain instead of like kind of many people. Like you mentioned the challenge for workforce development. So since this kind of as we near the end of our conversation, what would you say to our future students? For example, what would you say to our like Cornell system engineering, both so far we only have graduate degrees. We have Master of Engineering, Master of Science, and PhD in systems. We have a full spectrum of this graduate education because we believe that for system education, we can advocate for this T-shaped knowledge structure, right? Students will already have their undergrad major trained in some specific area, and then we come to a system engineering program so that they develop all these different system views and become equipped with all these different system tools and methodology to work transdisciplinary. But for these kind of people and students, what would you say, based on our discussion, both the challenge and needs of quantum computing? Because I believe this will be a very exciting area.
Oh, I very much agree with you. I think for new students coming in, there's two things that I can think of that are, I think, mirror exactly the approach the systems is taking to this. First, they need to be open to a broad conversation. Quantum computing is very early in its development, and all the way from the qubits and the devices and the interfaces up to the systems level, you need to have some understanding of that. That's many different topics. That's physics, electrical engineering, computer science, applications. But you also, if you want to succeed in this area as a professional, you need to pick which part of this system you want to be an expert in. And right now, those different communities are very disjoint. You have to be willing to force that conversation. Make the computer scientists talk with the physicists. They very much care about the same thing, but be the person that drives the conversation between those two communities. This is how you can help accelerate the development in the area, even before you yourself have learned everything that's going on. So I think that's a great place to start for people just getting going, and even for those people who are already working in the field. Continuing to improve our communication and our interactions with each other is something that's going to eventually lead us to success.
Wonderful, that's great advice. So my final question, I know you will be delivering a seminar talk later. So But with all this conversation, I believe you've got so many people interested in quantum computing. Can I take the privilege to peek into what you are going to be talking about in your talk? So maybe kind of this can probably lead our audience, because your seminar talk will also be made available on the Cornell website. Maybe you can say a few things about what your talk is going to be about, so that other people.
Oh,
yeah.
Absolutely, no. So the title is Scientific Computing with Quantum Computers, and it's really addressing the question of how can quantum computers help us accelerate scientific discovery. Right now at Oak Ridge, we use the world's fastest supercomputer called Summit for modeling and simulation across a variety of problems in chemistry, physics, materials. If we want to use quantum computers for that, there's a lot of work to be done developing applications that can run on those quantum computing systems. This talk is going to talk about two, one for chemistry and one for material scientists, or material science, and give you some early results that indicate that not only that it's feasible, but that it may actually eventually give us very good insights that we can't get any other way. So if you want to hear more, you have to watch the rest of the talk.
That's great, wonderful. So I will go downstairs, participate in your talk. But this is great. Of course, I think. Do you have any questions for me or anything? Otherwise, I will just go down, get things ready for a talk.
Wonderful. No, Oliver, this has been wonderful, and I think I'm really excited to hear about the systems effort that's underway at Cornell, because I think that is perhaps specifically the type of issue that quantum computing needs. As a technology, to move that, to migrate that into something that's useful, somebody has to be putting these pieces together. So it'll be exciting to have future conversations with you. So.
Wonderful. Thank you.
Thank you. Appreciate it, Oliver.